All right, last day of 3.5 coming your way, and now we're going to be talking about Newton's law of cooling. Probably of all of the things that we do with exponential growth and decay and logarithms in their own case, I think this one is pretty much the coolest one when it comes to that. It is a little difficult to understand at the beginning, but the better off you get once you try some of these things. Review questions again that are out here in front of you. Ultimately are still talking about solving exponentials. We really keep hammering the same idea over and over again and talking about domains. This one happens to have a relatively interesting domain of x squared minus 4, which I think of as x minus 2x plus 2 because it is a difference of squares. And as we well know, logarithms have to be greater than or equal to 0. Logarithms don't like 0 or negative numbers in any way, shape, or form. The easiest way to think of this particular domain would be to think that you're ultimately going to get these two ideas or roots going to be on the number line between 0 or between negative 2 and 2, and you're really asking when is that particular interval going to be greater than 0 or positive, and it's going to be positive on sections that are less than negative 2, because if we picked numbers relatively large and negative, they'd exceed the negative minus 4, or greater than 2 going the other direction. So our domain in this case would be only those intervals that would satisfy that, from negative infinity up to negative 2, non-inclusive of it, unioned with 2 to infinity. And the best way to think of those kind of questions is definitely on an interval kind of concept. The second and third questions are really about isolating exponentials and solving them. So isolate the guy first. We get e to the x is equal to 11, and we'd solve that question with an ln, or ln of 11 would equal x, and that's how you'd solve the second one. The third one that's listed there would be solved. Isolate the exponential again. It's already isolated. So you'd solve this one with a common log or a regular log, and that'd be the log of 5 of 11 is equal to 2x minus 1. And again, you could change the base formula to figure out what log 5 of 11 is and add your 1 and divide by 2. These should be skills by this particular time that are extremely capable of at this point in time, because it's the major part of the unit. Writing down the exponential growth and decay formulas that you've been seeing in the past. So a sub final, I'm going to put a sub f, is going to equal a sub o times e to the kt. And we've been working with this one for quite some time, but it's saying here that we should leave some space right after a sub o and the final and the initial. Now, what that turns out to boiling down to is we start talking about final and initial temperature concept. If I basically leave a little bit of space, and I'm going to say that this actually came from T sub final minus T sub r is equal to T sub o minus T sub r times e to the kt. Now, what they're going to do here is they're basically saying, let's say that you were having something that was going to cool. And as we've seen things that have cooled in the past, we've seen things like you take a set of muffins out of the oven. Oh my God, I'm having a brain fart. And it would ultimately cool down. Now, without any kind of restrictions on how that cooling takes place, ultimately, any kind of decay of cooling would ultimately mean that the muffins would end up down here at absolute 0. And that isn't what happens. We don't take our muffins out of the oven and they end up freezing. They end up cooling to a point where they're at the temperature of the room. So what we're really doing is that we're removing this concept of it making it to absolute 0, but there's this temperature concept that it reaches down to, and absolute 0 isn't achieved, but room temperature is. And that ultimately generates a new horizontal asymptote, and doing so, we've put in this horizontal asymptote into the question or the room temperature that's being taken place. And that right there, that particular equation that you're seeing right there, extremely relatable to the original decay formula, takes into consideration an initial temperature when it comes out, a final temperature that it's going to be when it's at the end, but takes into consideration that the room temperature is the lowest possible value that it'll ever reach to. And things do this. They decay and they cool at a rate that's exponential. That's why when you take the muffins out of the actual oven, they don't stay 350 degrees for an hour and a half. They cool relatively quickly, and then they cool to room temperature once they've been removed, okay? Now, this Newton's law of cooling really does have a lot of really cool ideas that are associated with it. The formulas that you see up above, you could use these formulas to specifically solve for any one of the individual values. Now, I relatively do not do this, okay? I will pause the video and write what those two are, but I don't write them as K and T. I am a firm believer that the formula and moving things in terms of algebra is a much better way to understand how the Newton's law of cooling is rather than memorizing some individual formulas. But I'll pause and I'll write down the K and T formulas. Now, ultimately, what I did in both of those individual formulas that I listed down here below was I subtracted the rate, the temperature of the room to one side. That gave me this piece upstairs, divided by the T sub O minus T sub R underneath, and then realized that to solve for E, I'd have to take the ln of both sides, and then the T would divide, or the K would divide on either side. Now, as I said, rarely will I see people that memorize these formulas to find T or to find K, because ultimately it's an algebraic process and I'm not really concerned about it. If you're really looking for that final temperature, that was the one that I wrote up above, that T sub F. And to find that T sub F, you take the room temperature and you add it to the initial temperature minus the temperature of the room times E to the KT. That's your Newton's law of cooling that we're going to be using here in just a few minutes, okay? Now, one of the ways we're going to do this is we're going to try it on just a baking problem, and then I'm going to show you that there is actually a forensic way of using this particular formula as well too, which is really fascinating. It's got some cool things to it. So Tyler Fay, he enjoys baking bread, so he decides to make some delicious Irish bread. Good for him. And he puts the bread in a 325 degree oven. Now, we're going to kind of highlight things as we go along here and understand what they really mean. The oven temperature that you're putting it in is exactly the temperature that the bread would come out in the initial amount. So this is T sub O. You're talking about 425 degree bread once it was removed. Time is going to be fairly important, so we're going to see how that plays into it. He bakes it for 40 minutes. That's another piece of information. And when he takes it out, he lets it cool for 15 minutes to a degree of 190 degree temperature. Now, 15 minutes is another time structure that we got to work on, but this is the temperature final that he ended up with, and the kitchen is at a 68 degree temperature. That's the temperature of the room. Now, here's what the whole premise is behind this. In no way, shape, or form did they give us in any of that part of the question K. K is missing. You do not know what the temperature rate of decay is going to be in this case. So this really falls down into the same exact questions that we've seen in the past, is that number one, you have to find K first. So this is a number one concept in any one of these Newton laws of cooling, is you've got to find K. So what we're going to do is we're going to set up the question with this information that's been set up and the 15-minute time cycle that it took for it to decay to that particular value to come up with the K value. Then we can work on the secondary question of what happens at 4 minutes. So finding K. Temperature final, 190 degrees. Equals, now I'm going to kind of move this up so you can see the formula up above, is going to equal the room temperature, 68 degrees, plus the initial temperature minus the room, which is 425 minus 68 e to the k. And in this particular case, I'm going to use 15 as my time. And I've got to keep in mind that my k value is going to come out being figured out in terms of minutes. Okay, now with a little bit of algebra that's associated with this, we would ultimately subtract, then divide, and then take our ln. We're kind of working our way towards that k, and it would end up looking something like this. The ln of 190 minus 68 divided by 425 minus 68, and that particular value would be the subtraction, the division, and the ln, but ultimately we would divide the answer by 15, and we'd get the answer for k. Now, just like we've done in the past, getting this k value is super important, and we're going to take that concept and put it in our calculator. The ln of, now this is where parentheses could be really helpful, 190 minus 68, and then I'm going to take that answer and divide by another set of 425 minus 68 as well. Close my parentheses the number of times, and take this ln and divide that answer by 15. And this will generate my k value. Store alpha k. Now, second question. What is the temperature going to be 4 minutes from now? Now, that question was only to find the k value. Here comes part 2. Part 2, the question says what's going to happen 4 minutes. Well, what's the temperature final going to end up being? Because we don't know what it is. That's the temperature of the bread after 4 minutes. But now we've got to go to the other parts. 68 plus 425 minus 68 e to the k, but the time is going to be 4 minutes. And ultimately, everything on this particular side of the equation is just plug and chug. 68 plus, and this will ensure that the actual answer, no matter how low it gets, it'll never go below 68 degrees because that's the room temperature. That's why that decay never gets lower than 0, never becomes negative in this case. That's going to be 425 minus 68 times second e to the 4 alpha k, and you've got an answer of 336.11 degrees. It's lower than the temperature that it came out of the oven, but it is not going below the temperature of the room, okay? Now, those are the two basic ideas of the questions. One, finding K is absolutely the very first necessity, and then finding that final temperature afterwards. Now it says, he would like to eat the bread when it's exactly 130 degrees. Apparently this is the perfect temperature for Irish bread. As we've all known, you eat a cookie at just the right temperature. The cookie tastes better than when you wait for it to be rock hard at room temperature. So how long does he need to actually wait? Well, by the time he finishes this problem, the bread's probably already cooled. But he's trying to figure it out. 130 is the final temperature that he's searching for. 68 plus 425 minus 68 e to the k t. And he's solving for t in this particular case. Again, it's all based on algebra. We'll subtract 130 minus the 68. We'll divide by 425 minus 68 underneath. To get the e to disappear, we take the ln of both sides, and ultimately we'd have the ln would equal kt, and we know k, we can divide it in. Let's find out how much time Tyler needs to wait. So this is the ln of 130 minus 68 divided by another set of parentheses of 425 minus 68 again, close it twice. Take this answer and divide by alpha k, and we've got an answer for time. He should wait 24.45 minutes before he actually bites into it at 1:30. Okay? Now, basic idea is that the cooling concept is really there to ensure that it never really gets below room temperature. And that's how that process works. Now, something that we've used this for in the past And my brother-in-law works for the RPDs. Talked to the forensic guys. Then they use this surprisingly very efficiently to figure out times of death. So we're talking about Mason and Garrett are strolling through Idlewild Park. Now, first off, they're strolling through Idlewild Park, and the time of day happens to be 2:31 p.m. So they made it all the way to the park 1 minute after school had ended. So we know for a fact that these two guys are ditching seventh period. Okay, that's what I'm seeing it as. I'm a detective as well, too. It is a perfectly 75-degree spring day, and unfortunately, but I would say not surprisingly, they discover a dead body. It is Idlewild Park. Yeah, it's a dangerous place, guys. Be careful down there. They discover a dead body, but Mason, who happens to be interested in forensic and is quite possibly taking some sports med from Miss Roming or maybe Miss Lucas and taking some anatomy and physiology, he pulls out his handy-dandy meat thermometer to test the temperature of the body, and he tests the temperature to be 97.6 degrees. Now, as Mason, temperature. There's a temperature that he got there. Temperature initial. Okay, now maybe not temperature. Well, we'll just say temperature at this point in time. We're not sure that's the initial. He measures the actual temperature 1 hour later because apparently Garrett's like, what do we do? They're going to send us to prison. Okay, they measure the temperature again later, 1 hour, another temperature reading at 96.2. Now, this is exactly what the coroner does when he arrives at a scene. He will take the temperature of the particular body, the victim, and then they will wait a certain amount of time and they will take the temperature again. The cooling process still continues until the body's at room temperature. At what time did the body die? So we've got looking for a time period that's going on here, and assuming that normal body temperature is 98.6 degrees. Now I'm going to make sure I check that just a second. I'm going to make sure that that's right. And see, I check my sources. Look at that. It's 98.6 degrees. I got that one. Way to go, G. Okay, 98.6 degrees. Now, the process of this problem is really a mathematical decay. And if we're going to do any part about this, we've got to get K first. That's going to be number one priority. So, you're walking around in the park. Your initial temperature, no matter what, should be around 98.6. So if I was setting this problem up with the initial temperature, it would be that the initial temperature was 98.6 degrees minus the 75 degrees for the outside part. That's where the initial temperature is going to be. Now, the first time that Mason sticks the body, he gets a 97.7 degree temperature out of it. And now wait a second. He has to use the two temperatures that he knows. He can't work it backward to the 98.6 yet. So he has to use the two temperatures that are known, which are 97.7 and the 96.2. He has to use two temperatures that he has measured to be able to find out what the decay rates are. That makes sense. E to the K, and the time that's taken place in this case has been an hour. But I'm going to say that things go by relatively quickly in terms of minutes here. So I'm going to say maybe that we should write this as 60 minutes. Okay, now solving this particular question, we're going to get a K value for it. So ultimately, we're going to take this particular idea, we're going to move it over here by... No, we have to take the initial temperature off of this one too as well. Sorry, made a mistake. I got to fix this. Gee, come on. You're messing it all up. Let me go back to black here. 96.2 minus the 75 degree temperature. Now, that normally would be in the front, so I subtracted it already. This would divide. So I'd end up with the ln of 96.2 minus 75 divided by 97.7 minus the 75, and then I would end up dividing that answer by 60 minutes and I would get K. Well, let's find out what that K value happens to be. I'm going to pause just so I can do the math. Nah, I won't pause. That's the ln of 96.2 2 minus 75. And then I'm going to take that answer, divide by 97.7 minus the 75. And I'm going to get the ln. I'm going to divide that by 60. And it's exactly what I'd expect, that the k value is a negative value, negative 0.001139, something like that. Okay? Again, I'm going to store this as alpha k. I'm pretty sure I'm going to come back to this. Okay? Now, you found your k value. Second problem is that they want to work out what time did the body actually die. That'd be the most important time, so that they can absolve poor Garrett and Mason from doing the crime. So let's find a way to work it backwards. Well, initially, you're walking through the park, temperature would be 98.6. And then we would actually work out that that's minus 75 would equal. Now, taking into consideration the temperature that was read at the end of this, okay, that would be the initial temperature would be, man, I keep getting this backwards. Man, it's the initial temperature again, sorry, and the finals over on the other side. 96.2 minus 75. This is 98.6. We're working it backwards to get back to the initial temperature when you were alive. You, I don't mean you, K, and I'm raising it to the T so that I can figure out how much time went by for it to come down to that particular temperature. Now, if it's beyond an hour, Mason and Garrett are pretty in good shape, okay? And it should be, because when he tested it, it was 97.7. So it better be, in that particular case, more than an hour's time span. Again, a dividing concept, an ln, and we should be able to divide the answer by k and get the time that the person died. So here we go. ln of 96.2 minus 75 divided by 98.6 minus 75. And then I'd take that answer and divide by k, and I'd get the time. Now let's see if we've absolved them from the crime. Please, please, I don't want to see these kids go to prison. ln of 96.2 minus the 75 divided by 98.6 minus the 75, close it twice, and then divide this answer by alpha k. And ultimately, we're looking at 94.12 minutes. So it was longer than an hour ago, and if we start to work the process back, he took that temperature at 97.7 at 2:31. We know for a fact that he took this latest temperature at really 3:31 is when that temperature was. So if we take 3:31 and we work it backwards, we can figure out what time that actually took place. Not really good at working the clock backwards. Let me get a second and we'll figure this out. So I worked back the actual process of elimination. I did an hour to back to 2:31. That's when they actually found it. And then there was an extra 34 minutes beyond that. So 31 off of that would make it 2 o'clock. And an extra 3 minutes would make it right around 1:57 is when this particular thing took place. And that is exactly how the forensic people decide on how far back the body died in that particular case. They use a Newton's law of cooling concept. You're really not much different than a muffin. You're just, a dead body at that point in time. All right, so try these problems out. Again, re-watch some of this stuff that I do because, I make simple mistakes too as well. And if you can highlight those places where maybe I've even struggled a little bit and get the numbers in the correct place, you can really do a good job on this. All right, good luck. Newton's law of cooling is waiting for you, and let's be forensic scientists.